In just a few weeks, NASA will launch what could be the most powerful space telescope ever built for surveying the cosmos. The Nancy Grace Roman Space Telescope is scheduled to lift off on August 30, 2026, and it promises to transform our understanding of the universe from the smallest exoplanets to the largest cosmic structures. Named after NASA's first chief of astronomy, Nancy Grace Roman, who was instrumental in the development of the Hubble Space Telescope, Roman is a next-generation infrared observatory with a field of view 100 times larger than Hubble's. That means it can map vast areas of the sky in a fraction of the time, making it the ultimate cosmic survey instrument. The telescope is built around a 2.4-meter primary mirror, the same size as Hubble's, but donated by the National Reconnaissance Office. This mirror was originally designed for classified spy satellite programs, but now it will be used to unlock the deepest secrets of the cosmos. Combined with a shorter focal length than Hubble's, the mirror provides a much wider field of view that is ideal for large-scale surveys. Roman carries two main scientific instruments, each designed to tackle different questions. The Wide Field Instrument, or WFI, is a 300.8 megapixel camera that captures visible and near-infrared light across an enormous area of the sky. It can take images as sharp as Hubble's, but covers a region 100 times larger in a single exposure. This instrument carries 8 science filters, 2 spectroscopy elements, and a calibration element, all mounted on a rotating wheel that allows scientists to choose exactly what wavelengths of light they want to study. The second instrument is the coronagraph instrument, or CGI. This is a high-contrast imaging system that uses advanced deformable mirror technology to block out the blinding light of stars, revealing the faint planets orbiting around them. The CGI achieves a part per billion suppression of starlight, making it possible to detect planets that are tens of millions of times fainter than their host stars. This is a technology demonstration for the future Habitable Worlds Observatory, which will one day search for signs of life on Earth-like planets. One of Roman's primary science objectives is to study dark energy, the mysterious force that is causing the universe to expand at an accelerating rate. Scientists have known about dark energy since 1998, when observations of distant supernovae revealed that the expansion of the universe is speeding up, not slowing down as gravity would predict. But more than 25 years later, we still do not understand what dark energy actually is. Roman will use 3 independent techniques to investigate dark energy. The first is baryon acoustic oscillations, which are faint ripples in the distribution of galaxies left over from sound waves that traveled through the early universe. By measuring the scale of these ripples at different cosmic epochs, Roman can track how the expansion rate of the universe has changed over time. The second technique involves observing distant type Ia supernovae, which serve as standard candles for measuring cosmic distances. Roman will discover thousands of these supernovae across a wide range of distances, allowing it to map the expansion history of the universe with unprecedented precision. The third technique is weak gravitational lensing, where the gravity of massive objects like galaxy clusters bends the light from more distant galaxies, subtly distorting their shapes. By measuring these distortions, Roman can map the distribution of both visible and dark matter across the universe, and see how structure has grown over cosmic time. Together, these 3 methods will help answer one of the biggest questions in fundamental physics. Is dark energy a new energy field that permeates space, or does Einstein's theory of general relativity break down on the largest cosmological scales? Roman may finally provide the evidence needed to distinguish between these possibilities. Another major goal of the mission is to complete a comprehensive census of exoplanets using a technique called gravitational microlensing. When a planet passes in front of a distant star from our line of sight, the planet's gravity bends and magnifies the starlight in a characteristic way. Roman can detect this effect for planets as small as Mars, including free-floating worlds that orbit no star at all. This technique is especially powerful because it can find planets in the cold, outer regions of planetary systems, where other planet-hunting methods struggle. It will tell us how common solar systems like our own truly are, and whether Earth-sized worlds in the habitable zone of their stars are rare or abundant throughout the galaxy. The microlensing survey will also detect a population of rogue planets, worlds that have been ejected from their solar systems and now drift through interstellar space. Roman's coronagraph will also directly image giant exoplanets, capturing their light and analyzing it with spectroscopy to determine the composition of their atmospheres. This could reveal signs of water vapor, methane, carbon dioxide, and other molecules that point toward potential habitability. For the first time, we will be able to study the atmospheres of planets around other stars in detail, comparing them to the gas giants in our own solar system. The mission builds on the legacy of both the Hubble Space Telescope and the James Webb Space Telescope. Hubble gave us deep images of tiny patches of sky, revealing the universe in unprecedented detail. Webb peers into the infrared with extraordinary sensitivity, seeing the first galaxies that formed after the Big Bang. But Roman will survey the sky at an enormous scale, connecting the dots between individual observations and creating a vast map of the cosmos. In fact, Roman will conduct surveys that would take Hubble hundreds of years to complete. Over its 5-year primary mission, it will image more than 1 billion galaxies, discover tens of thousands of new exoplanets, and map the structure of the Milky Way in unprecedented detail. It will also study the formation of galaxies, observe the cosmic web of dark matter that connects all structures in the universe, and investigate the life cycles of stars. The telescope will also search for primordial black holes, hypothetical objects that may have formed from density fluctuations in the first moments after the Big Bang. If detected, these tiny black holes could provide evidence for new physics beyond the standard model, potentially revealing the nature of dark matter itself. Roman's microlensing survey is uniquely sensitive to these objects. Roman's journey to space has been a long and challenging one. It was first recommended as the top priority for the next decade of astronomy by the National Academy of Sciences in 2010. It was officially approved for development and launch on February 17, 2016. Over the years, it faced repeated budget challenges and even multiple threats of cancellation from the Trump administration, but it survived each time thanks to strong and unwavering support from the scientific community and Congress. Construction was completed on November 25, 2025, and the telescope arrived at the Kennedy Space Center in Florida on June 21, 2026. The satellite bus, which carries the telescope and all its support systems, was substantially completed in September 2024. The instruments and mirror assembly were successfully integrated onto the instrument carrier in December 2024. Now the telescope sits in a clean room at the Kennedy Space Center, waiting for its ride to space. Roman will launch aboard a SpaceX Falcon Heavy rocket, one of the most powerful launch vehicles currently in operation. The launch contract, valued at approximately $255 million, was awarded in July 2022. The Falcon Heavy is capable of sending Roman directly to its destination with the required precision. The launch window opens on August 30, 2026. Roman will head to a point in space called Sun-Earth Lagrange Point 2, or L2, located about 1.5 million kilometers from Earth in the direction opposite the Sun. This is the same region where the James Webb Space Telescope operates, offering a stable thermal environment, a clear view of the cosmos without interference from Earth's atmosphere, and efficient communication with ground stations. Once operational, Roman will begin a 5-year primary science mission, though its fuel reserves and component lifetimes could allow it to operate for a decade or longer. Every day, it will send down terabytes of data, more than any previous NASA astrophysics mission. This vast data stream will be processed and made publicly available, allowing astronomers around the world to make discoveries in real time. This open data policy represents a major shift from previous missions, where data was often proprietary to the observing team for a year or more. With Roman, the entire astronomical community will have immediate access to the most comprehensive survey of the universe ever conducted. This will democratize space science and accelerate the pace of discovery. Roman's wide-field capabilities will also serve as a finder mission for other telescopes. When Roman spots something interesting, such as a distant supernova, a gravitational lensing event, or a potential exoplanet, the James Webb Space Telescope and ground-based observatories can follow up with detailed observations. This synergy between observatories will maximize the scientific return from every discovery. The coronagraph instrument on Roman is particularly exciting because it is a technology demonstrator for the next generation of space telescopes. The deformable mirror technology and starlight suppression techniques that CGI tests will be essential for the Habitable Worlds Observatory, a future NASA mission currently in the planning stages. The Habitable Worlds Observatory is designed to directly image Earth-like planets around nearby stars and search for signs of life in their atmospheres. Nancy Grace Roman, the telescope's namesake, was known as the mother of Hubble. She fought tirelessly for space-based astronomy at a time when the idea was considered radical by many in the scientific establishment. She became NASA's first chief of astronomy and played a key role in convincing Congress to fund the Hubble Space Telescope. It is deeply fitting that her namesake telescope will carry on that legacy of bold exploration, pushing the boundaries of what we can see and understand about the universe. The Roman Space Telescope represents a fundamentally new approach to astronomy. It is not designed to look at a single star or galaxy in exquisite detail, as Hubble and Webb do. Instead, it is designed to map the entire universe on a massive scale, creating a comprehensive picture of cosmic structure, dark matter, dark energy, and the population of exoplanets that fill our galaxy. It will create a vast catalog of billions of objects, from asteroids in our own solar system to the most distant quasars at the edge of the observable universe. This catalog will serve as the foundation for astronomical research for decades to come, enabling discoveries that we cannot even imagine today. For dark energy, Roman could provide the evidence needed to confirm or refute our current theoretical models. If dark energy turns out to be something other than Einstein's cosmological constant, it would revolutionize our understanding of fundamental physics. For exoplanets, Roman could reveal that the galaxy is teeming with billions of worlds, many of which might be capable of supporting life. The countdown has begun. In just a few weeks, the Roman Space Telescope will begin its journey to Lagrange Point 2, and the universe will never look the same again. This is more than just a new telescope. It is a new window into the cosmos, and it is about to open for the first time. The next great chapter in space exploration is about to begin.